All right, let's discuss how to make an inference on correlation coefficient. Well, first of all, what is an inference and why we need it? On this plot, you can see that we have two variables, x and y, and the gray points, all these gray points, right? So these are points for population. The red points are my sample. I have a sample size of 30 in this case. And this is my sample. Why they are red? Because if you look at these dashed lines, it's average values. And then you can see that all these red points, they will contribute positively to the covariance and therefore to the correlation, right? Now, if I compute correlation for my population, it will be 0.967. And of course, it's fixed because I don't change the population. If I compute the correlation for my sample, for the red points you see here, I will get a quite bigger number, 0.982. Oh, sorry, it's 20, not 30 values, okay? So it means that the correlation of my sample is not the same as the correlation of the population because it's a sample statistic. You remember, any sample statistic is a random number, which depends on the sample size, right? So in this case, I kind of overestimate correlation because I get a higher number than it is. However, if I take a new sample, I will get a smaller number. Now the correlation is 0.95, although the population correlation is 0.967. If I take a new sample, a new sample, a new sample, you will find out that every time you take a new sample, the correlation coefficient will be slightly different. Sometimes it will be below the real correlation. You can see way below. Sometimes it will be above the real correlation. When I say real, it means the expected value, the population value, right? So how to solve this problem? How to find out what's the population correlation is if we know the sample correlation? Well, that's what we did in block number 2 for average values and for variances, right? So we know how to compute, for example, confidence interval. We just need to know distribution. So how R distributed around rho. So this is a Greek letter rho. You remember we use Greek letters for population. So this is a population of the correlation coefficient for population rho. Okay. Now let's discuss it. So first of all, we need to know distribution, how R distributed around rho, how far it can go from the true correlation coefficient, what this variation depends on, and also how to estimate rho if you know R, how to estimate, how to make this confidence interval. Let's discuss it. Well, first of all, let's investigate how the distribution looks like. In this case, I took a population with correlation 0.96. It's a lot of values. You can imagine that you have x and y, this matrix with two variables, x and y, and then, for example, the number of rows is 1 million. Okay. Then I will take a sample from this matrix, just sample, in this case it's rows, particular rows, random rows. And then I will compute correlation for these selected rows between x and y and make a plot. Let me show you the results. So this is distribution histogram when the sample size is 5. So I take 5 random rows out of 1 million and then compute correlation. You can see although the true correlation is 0.96, it's shown here as a red line. The variation is quite big, and you can see this distribution histogram doesn't look like any distribution we already know. It doesn't look like normal or t-distribution. It doesn't look like chi-square distribution. So distribution is completely different. That's sad, but we will see what we can do. You can see quite a big variation between 0.7 and 1, although the true correlation is 0.96. However, you can see most of the values are here, so around the values that we actually know. If you take a sample of a higher size, in this case 10, you can see that the shape of distribution is more or less the same, but it's more narrow, right? So you can see that the variation is smaller. If you increase further the sample size to 30, it's even smaller. So now it's between 0.9 and 1. Now it's kind of good, right? If you increase the sample size even further, like 100, you can see it's very tiny. So definitely the variation, how far R can go from rho, depends on the sample size. That's what we also know from the other statistics for average, for standard deviation, for variance, right? The higher the sample size is, the larger sample size is, the less uncertain you have. So the closer your sample represent the population, and therefore the uncertainty is smaller. Okay. So this is just a zoom in. You can see that it's for the last case when sample size is 100. You can see the variation is very small, right? So the true value is here, and you can see that the variation is very small indeed. Okay. Now, what happened if the population correlation coefficient is moderate? So in this case, you can see it's around 0.6. So it's not very strong correlation between X and Y. Will it influence anything? Well, it will. Look, this is sample size 5, and now you can see it really got bananas, right? So it goes from -1 to +1. So it's really uncertain. If you have 10, it's a little bit better, but still you can see we have some values which are negative, some values which are positive. So it's way far from the true 0.57. Imagine that you got -0.2, you will believe that the correlation is negative, but in fact the correlation is 0.6 almost. That's crazy. Now, if sample size is larger, however, you can see that the variation again gets smaller and smaller. And when the sample size is 100, it gets moderately narrow, right? So in this case, from 0.3 to 0.7 approximately. So correlation itself influences this uncertainty. The smaller correlation is, the bigger uncertainty is. So now we know the answer for the two first questions, right? So we know that the variation of R, how far R can go from rho, it depends on two things. It depends on the sample size, and that's kind of expectable, right? So this larger sample size, the smaller variation, the smaller sample size, the larger variation. But it also depends on the population correlation coefficient. So if you have a strong trend, if you have a high correlation, the uncertainty will be smaller, right? The problem is, we still don't know the distribution. And this distribution looks, you can see it's left skewed distribution, right? So we don't know what to do with this distribution. We have no idea which distribution to use. However, there was a famous statistician, Ronald Fisher, who empirically found out that if X and Y are distributed normally, so it means that if you look at distribution of X and Y for population, they will follow almost nicely normally distribution, right? If sample is taken randomly, and that's a kind of a common requirement for any statistics, and also if sample size is large enough, meaning at least 10 rows, at least 10 individuals, then you can make a trick. Instead of looking at correlation, you can convert correlation to a new statistic, which is called Z prime. This is how to convert it. Take your correlation coefficient, add 1, and then subtract from 1, take a ratio, take a natural logarithm, and take a half of it. Then this Z prime will follow normal distribution, and this will be the standard deviation of this distribution. So let me show you how it looks like. So if I take the original values, in this case you remember that I have different, I forgot to mention probably this. You can see I have different row and different sample size, right? So in this case row is 0.9 and sample size is 10. Here, row is 0.9 and sample size is 100. Here, row is 0.5 and sample size is 10. And here, row is 0.5 and sample size is 100, right? So we have like 4 different combinations. Now, again, this is distribution of correlation coefficients of my samples. I took many samples, computed correlation for every sample, and this is distribution of this correlation coefficient. Now, if I take all these computed R values and use this expression to turn them to this new statistic Z prime and make distribution of Z prime, this is distribution of Z prime. So instead of this, I got this. And instead of this, I got this. And instead of this, I got this. Look, in all these cases, the distribution look nicely as a normal distribution. And if it's normal distribution, we can compute the confidence interval. So we can find Z prime low, we can find Z prime high, right? And that will be confidence interval, for example, 99 or 95% confidence interval. So that's the basic idea. So you go from R to Z prime, compute the confidence interval there, and then recompute this interval back to get the row. Okay, so this is the overall idea. Now, before we continue, I recommend you to go to Grasta and play with this app. It's a population-based CI. It shows you exactly how far R can go from rho, from different sample size, for different correlation coefficient, and so on and so forth. So first of all, watch a short video, introduction to this app, then go to app, play with this app, and you will be much more confident, and the next block will be a little bit easier. Okay, so watch the video, play with the app, and come back.